Oxford, England, February 12, 1941. In a sterile hospital room at the Radcliffe Infirmary, a 43-year-old police constable lay dying. Albert Alexander's face was unrecognizable, covered in abscesses that had already claimed one eye. The infection crawled beneath his skin like fire, spreading from a scratch he'd received months earlier while pruning roses. Sulfa drugs, the most powerful weapons medicine had against bacterial infection, had failed. His lungs harbored smoldering pockets of pus. His shoulder joint swelled with infection. Every breath came harder than the last. Howard Florey stood at the bedside holding a vial of brownish liquid. It contained 160 milligrams of a substance extracted from common mold, something most of his colleagues dismissed as laboratory curiosity. For 12 years, this mold juice had been ignored by the medical establishment. Fleming had discovered it by accident, published his findings, then watched as the world turned away. But Florey believed. He had to believe because Constable Alexander was out of options. The needle pierced the vein. The brownish liquid entered Alexander's bloodstream. Then came the waiting. 24 hours later, something impossible happened. Alexander's fever broke. His appetite returned. The angry red inflammation surrounding his eye socket began to fade. He sat up. He spoke. He asked for food. The nurses whispered among themselves. They had seen men this far gone. They never recovered. Never. Yet here was Albert Alexander, eating breakfast, joking with the staff, his body pulling itself back from death's doorway with a speed that defied every rule of infection medicine had learned in centuries of practice. Florey's team worked around the clock. They collected Alexander's urine, extracting every molecule of penicillin that passed through his kidneys, purifying it, preparing it for re-injection. The war had strangled their supply lines. The equipment they needed didn't exist. Everything had to be improvised, jury-rigged, coaxed into existence from laboratory glassware, never designed for pharmaceutical production. By the 5th day, Alexander looked almost healthy. The abscesses had drained. The inflammation had retreated. His remaining eye showed clarity and focus. Then the penicillin ran out. The infection, beaten back but not destroyed, sensed the chemical pressure lifting. It surged forward. Within days, the abscesses returned, angrier than before. Alexander's temperature spiked. On March 15, 1941, 31 days after receiving the first dose of penicillin, Albert Alexander died. Not because penicillin failed, because there wasn't enough of it. Florey stood in his laboratory that night, surrounded by fermentation vessels and culture plates, and made a decision. This would never happen again. The story had begun 13 years earlier, in a moment that looked like carelessness, but was actually preparation meeting opportunity. September 1928, St. Mary's Hospital, London. Alexander Fleming returned from vacation to find his bacterial culture plates contaminated. Most researchers would have cursed, sterilized the plates, started over. Fleming looked closer. Around one particular contaminating mold, the bacterial colonies had died. Not just stopped growing, died. A clear zone surrounded the fuzzy mold colony, a kill zone where nothing survived. Fleming was no stranger to the problem of bacterial infection. He had spent World War I as a captain in the British Medical Corps, watching men survive artillery wounds, only to die days later from bacteria that turned healthy tissue into gangrenous slime. He had tested antiseptics, measuring their effectiveness, and discovered something disturbing. The antiseptics killed bacteria, yes, but they also destroyed white blood cells. He had watched doctors pack antiseptic-soaked gauze into wounds, creating sterile dead zones where bacteria that survived in tissue crevices could multiply unopposed by the body's immune defenses. 90% of the wound swabs he analyzed contained bacteria. The death rate from infected wounds in World War I had been catastrophic. Fleming had counted the cost in faces, names, men who should have lived. So when he saw that clear zone around the mold, he didn't see contamination. He saw possibility. He isolated the mold, identified it as Penicillium notatum, and began testing the broth in which it grew. The liquid killed Staphylococcus. It killed Streptococcus. It killed the bacteria that caused gas gangrene. It did this without harming human tissue. Fleming published his findings in 1929 in the British Journal of Experimental Pathology. The paper described a substance that could destroy bacteria without poisoning patients, a chemical that passed through the body and could be recovered from urine. It was revolutionary. It was world-changing. Nobody cared. The scientific community shrugged. Penicillin was too unstable, they said. It lost potency within days of extraction. It couldn't be purified. It couldn't be concentrated. It couldn't be mass-produced. The chemical structure was unknown. The optimal growth conditions were unclear. Fleming himself struggled to produce useful quantities. His lab lacked the biochemical expertise needed to stabilize and purify the compound. The mold grew slowly. The yield was low. The active ingredient broke down faster than it could be extracted. By the mid-1930s, Fleming had largely abandoned clinical research on penicillin. The mold juice sat on laboratory shelves, a curiosity, a footnote, a road not taken. Then came 1938. Howard Florey, newly appointed professor of pathology at Oxford University, was looking for research projects. Florey was Australian, blunt, driven, methodical. He had built the Sir William Dunn School of Pathology into a research powerhouse. Ernst Boris Chain, a Jewish biochemist who had fled Nazi Germany, suggested revisiting antibacterial substances. Chain had read Fleming's 1929 paper. He saw what others had missed, not a clinical impossibility, but a biochemical challenge. The team Florey assembled was small, but formidable. Chain handled biochemistry. Norman Heatley, a fungal expert, tackled the problem of growing penicillium in quantity. They scavenged equipment. Oxford University had no funding for pharmaceutical research. The war was approaching. Money was scarce. Heatley improvised fermentation vessels from bedpans, bathtubs, hospital urinals, anything that could hold liquid and wouldn't poison the mold. The laboratory filled with ceramic containers, each one nurturing a thin film of mold on the surface of culture medium. The extraction process was agonizing. Penicillin existed in the broth at concentrations of less than 1 part per million. They had to filter the mold, adjust the pH, extract the penicillin into organic solvents, then back extract into water, then freeze dry. Every step lost material. Every delay allowed degradation. They worked through the night, sleeping in shifts, timing their extractions to catch the penicillin before it broke down. By early 1940, they had enough crude penicillin for animal tests. May 25, 1940. The experiment that would change medicine happened on a Saturday because the work was too urgent to wait for Monday. 8 mice, each injected with a lethal dose of Streptococcus bacteria. 4 received penicillin, 4 received nothing. By Sunday morning, the 4 untreated mice lay dead in their cages. The 4 treated mice were alive, active, apparently healthy. The pattern repeated with larger groups, different bacteria, same result. Penicillin worked. It worked consistently. It worked without poisoning the animals, but a man weighed 3,000 times as much as a mouse. Florey needed to scale up production before human trials could begin. The team moved operations into a larger space, installing more fermentation vessels, hiring assistants to tend the cultures around the clock. By January 1941, they had accumulated enough penicillin to test for human toxicity. A volunteer received an injection and experienced no ill effects. The safety threshold had been crossed. Now they needed a patient desperate enough to try an unproven drug. Albert Alexander had been that patient. His dramatic improvement, followed by his death when supplies ran out, proved 2 things simultaneously. Penicillin worked. And producing enough of it was going to require resources far beyond what a university laboratory could provide. Florey contacted pharmaceutical companies in Britain. The war had disrupted everything. Factories were producing explosives, not antibiotics. The response was polite, but discouraging. Britain couldn't scale up penicillin production while fighting for survival. Florey made a decision that would alter the course of the war. He went to America. In June 1941, he and Heatley flew to the United States, carrying culture tubes of Penicillium notatum smeared on the lining of their coat pockets. If their plane went down over the Atlantic, if German agents searched them, the most important substance in modern medicine would look like dirt stains. They landed safely. They made their case to the United States Department of Agriculture Research Laboratory in Peoria, Illinois. The Americans brought industrial thinking to a biological problem. The Peoria lab tested thousands of mold samples, looking for high-yielding strains. They found one growing on a cantaloupe in a local market. This strain produced 200 times more penicillin than Fleming's original sample. They experimented with culture media. Oxford had grown the mold on synthetic broth. The Americans tried corn steep liquor, a waste product from cornstarch manufacturing. Yields increased tenfold. They abandoned surface culture, where mold grew as a film on liquid. Instead, they used deep fermentation in huge vats with forced aeration. The mold grew throughout the volume of liquid, not just on the surface. Production rates exploded. By late 1941, American pharmaceutical companies were building fermentation plants. Merck, Pfizer, Squibb, Abbott Laboratories all committed factories to penicillin production. The United States War Production Board made penicillin a top priority, second only to the Manhattan Project. In March 1942, Ann Miller, a 33-year-old woman dying of streptococcal septicemia in a Connecticut hospital, received a tablespoon of penicillin, half the entire supply available in the United States at that moment. She recovered fully, becoming the first American cured by the drug. Military testing began in early 1943 at Bushnell General Hospital in Brigham, Utah. Over 200 soldiers with war-related orthopedic injuries filled the wards. Most had compound fractures complicated by osteomyelitis, bone infections that Sulfa drugs couldn't touch. These men faced amputation or death. The doctors gave them penicillin, administering it by injection and packing it directly into wounds. They kept meticulous records, documenting dosages and side effects. The results bordered on miraculous. Men who had been deteriorating for months began to heal. Bone infections cleared. Wounds that had been oozing pus for weeks closed and formed healthy scar tissue. Surgeons found they could operate on injuries they had previously considered hopeless, cleaning and closing wounds that would have required amputation in any previous war. Word spread through military medical channels. In April 1943, Florey himself traveled to North Africa, where Allied forces were fighting Axis troops in brutal desert conditions. Battlefield wounds in North Africa were particularly horrific, contaminated with dirt, fabric, metal fragments, everything bacteria needed to thrive. Florey brought supplies of penicillin and a protocol for treatment. Instead of amputating damaged limbs immediately, he instructed surgeons to clean wounds thoroughly, remove dead tissue, then close the wound surgically and treat the soldiers with penicillin. The trials were spectacular. Men who should have lost arms and legs kept them. Chest infections that would have killed soldiers in previous wars resolved within days. Venereal disease, which had disabled entire units in World War I, became a treatable condition that returned soldiers to duty within a week. The mortality rate from bacterial infection in wounded soldiers dropped by 15%. 15%, thousands of lives saved by mold juice that medical authorities had dismissed as a laboratory curiosity. By late 1943, American factories were producing billions of units of penicillin monthly. British medical authorities, watching American success, scrambled to establish protocols for when the drug reached British hospitals. The emergency medical services identified hospitals that would receive casualties treated with penicillin at the front. They trained surgeons and pathologists in administration techniques. They designed a labeling system so wounded men who had received penicillin would continue treatment during evacuation. Patients bore yellow labels marked "Pen." They received injections every 4 to 5 hours during transport. The system had to be perfect because the drug was still scarce, still precious. In December 1943, only 9 hospitals in the United Kingdom had staff experienced in using penicillin. The military planners preparing for the invasion of Europe knew they would need more, many more. Estimates suggested 50,000 to 100,000 Allied casualties in the initial assault alone. Professor F.R. Fraser, the Ministry of Health's advisor on wartime hospitals, calculated they would need 5 billion units of penicillin per month. The current production was less than half that. Prime Minister Winston Churchill received reports in February 1944 showing that British production facilities would generate only 1/10 of projected output. He scrawled in red ink across the report, "I am sorry we can't produce more." Britain would depend on American penicillin to save British soldiers. The Americans, to their credit, delivered. Supply chains stretched across the Atlantic, cargo ships carrying crates of freeze-dried penicillin powder, more valuable than gold, more critical than ammunition. By May 24, 1944, less than 2 weeks before D-Day, Fraser could finally report that sufficient supplies of penicillin had reached Britain for treating battle casualties. Not enough for civilians. Civilian use remained prohibited. Every vial was reserved for military wounded. Hospitals received detailed instructions. Penicillin was to be dissolved in distilled water immediately before injection. Unused portions were to be passed to other medical officers, not discarded. The drug was too valuable to waste. Contamination had to be prevented absolutely because a contaminated solution could kill rather than cure. June 6, 1944. Dawn broke over the English Channel. More than 150,000 Allied troops approached 5 beaches on the Normandy coast. The largest amphibious invasion in history was underway. At Omaha Beach, American forces encountered devastating German fire. The geography worked against the attackers. The initial armored support failed to arrive. Men died in the water, on the sand, in the dunes beyond. But many men who would have died from infected wounds in any previous war survived. Medics carried penicillin powder in their field kits. They sprinkled it into wounds, then bandaged and tagged the casualties for evacuation. At field hospitals just behind the lines, surgeons treated the most severe cases, cleaning wounds that in World War I would have meant certain amputation or death, closing them surgically, then beginning penicillin injections. The wounded were evacuated to England by ship and plane, each one bearing their yellow pen label, each one receiving timed injections during transport. They arrived at coastal hospitals where staff trained in penicillin therapy continued treatment. Then they were transferred to regional hospitals near their homes, the treatment uninterrupted. The bacterial infections that had killed so many in previous wars held at bay by steady doses of mold extract. The system worked. Hundreds, then thousands of soldiers received penicillin for infected wounds. According to later estimates, penicillin reduced D-Day fatalities by 12 to 15%. Up to 15,000 men who would have died lived because of a drug that had been ignored for more than a decade. The impact extended far beyond D-Day. As Allied forces pushed into Europe through summer and fall 1944, penicillin went with them. Field hospitals used it routinely. The rate of amputations fell. Recovery times shortened. Soldiers returned to duty faster. The drug that had failed Albert Alexander because supplies ran out after 5 days was now available in quantity sufficient to treat entire armies. By July 1944, production had increased enough that restrictions began to ease. The War Office approved penicillin use for medical conditions in service patients and for air raid casualties among civilians. The wall between military and civilian medicine was beginning to crack. In September 1944, with Allied victory in Europe looking increasingly certain, administrators began planning for peacetime distribution. Who would receive the drug first? Which hospitals had trained staff? How would supplies be allocated? Penicillin became available to the British public in 1946. The drug that Fleming had discovered by accident in 1928, that Florey and Chain had purified through years of painstaking work, that American industry had learned to mass produce, was finally accessible to everyone who needed it. Pneumonia, which had killed millions throughout human history, became a treatable disease. Bacterial meningitis, almost always fatal, could now be cured. Syphilis, which had destroyed lives and families for centuries, succumbed to a 2-week course of injections. Childbirth fever, which had made hospitals more dangerous than home births, virtually disappeared. The revolution extended beyond bacterial disease. Surgeons could now attempt procedures that had been suicide before penicillin. Heart surgery became possible because post-operative infections could be prevented. Organ transplants became feasible. Cancer treatment could use more aggressive techniques because infection risk was manageable. The entire landscape of medicine shifted because doctors could finally control bacterial infection. Fleming, Florey, and Chain shared the 1945 Nobel Prize in Physiology or Medicine. The committee's citation noted that penicillin had already saved thousands of lives and would save millions more. Fleming gave speeches warning about antibiotic resistance, noting that bacteria exposed to subtherapeutic doses of penicillin developed resistance and passed it to their offspring. He was right, but that problem belonged to the future. In 1945, the present was miraculous enough. A substance dismissed as laboratory curiosity had become the most important drug in human history. The soldiers who received penicillin in North Africa, in Normandy, in hospitals across Britain, in field stations from France to the Pacific, numbered in the hundreds of thousands. Each one represented a life saved, a family spared grief, a future that would exist rather than end. Each one was a vindication of Florey's decision to persist when supplies ran out and Albert Alexander died. Each one was proof that Fleming had been right to look closely at that contaminated culture plate in 1928, to see possibility instead of error. The impact on World War II was profound. Generals wage war with armies, but armies are made of men. Men who can be healed return to fight. Men who die of infected wounds don't. The 15% reduction in deaths from bacterial infection among Allied wounded translated to tens of thousands of additional soldiers available for combat. It meant experienced troops returning to units instead of graves filling with men who survived the initial wound only to die from infection days later. Some historians argue that penicillin contributed as much to Allied victory as any weapon system. That claim is debatable. What's not debatable is that penicillin fundamentally changed the nature of battlefield medicine. But the true measure of penicillin's impact extends far beyond military statistics. Albert Alexander, the policeman who died because penicillin supplies ran out after 5 days, was the last person who would die for that reason. By 1944, production had scaled from laboratory beakers to industrial fermentation vats producing thousands of liters. By 1945, penicillin was being manufactured in quantities sufficient for both military and civilian use. By 1946, any doctor could prescribe it. The constraint that killed Alexander had been broken. The path from Fleming's contaminated culture plate to mass production had taken 16 years. 16 years during which the discovery sat on laboratory shelves, dismissed, overlooked, considered impractical. 16 years during which people died from infections that penicillin could have cured. The tragedy is that Alexander Fleming published his findings in 1929. He described penicillin's antibacterial properties. He noted its lack of toxicity to human tissue. The information was public, available to any researcher who cared to investigate. The lesson is not that Fleming was ignored. The lesson is that scientific discovery alone changes nothing. Fleming discovered penicillin. Florey and Chain developed it into a usable drug. American industry learned to produce it in useful quantities. Military Medical Corps developed protocols for battlefield administration. British and American governments coordinated supply chains and hospital training programs. None of these steps was inevitable. None happened automatically. Each required specific people making specific decisions at specific moments. If Florey had not read Fleming's paper, if Chain had not suggested revisiting antibacterial substances, if Heatley had not solved the production problems, if the American researchers had not found high-yielding mold strains, if pharmaceutical companies had not committed factories to production, if the War Production Board had not made penicillin a priority, if any of these had not happened, the drug might have remained a laboratory curiosity. Soldiers would have continued dying from infected wounds. Pneumonia would have remained a death sentence. Modern medicine would not exist in its current form. The photograph that accompanied many post-war penicillin advertisements showed a healthy soldier with the caption, "Thanks to penicillin, he will come home." The image was propaganda, simplified, designed to sell the miracle of modern medicine. But it was also true. Tens of thousands of soldiers did come home because penicillin treated their infected wounds. Millions of civilians lived longer because penicillin cured their pneumonia, their strep throat, their post-surgical infections. The drug that authorities had ignored for more than a decade became the foundation of antibiotic medicine, the gateway to an era when bacterial infection stopped being a death sentence. Fleming kept the original culture plate, the one contaminated with Penicillium notatum in September 1928. He showed it to visitors, explaining how he had almost discarded it, how a moment's curiosity had led to discovery. That culture plate is now preserved in the British Library, a relic of the moment when chance and preparation intersected to change medicine forever. It looks ordinary. A glass dish, some yellowed growth medium, a fuzzy patch of mold. Nothing about it suggests world-changing importance. But around that mold patch, if you looked closely in 1928, you could see a clear zone where bacteria had died, a kill zone, a space where something in the mold had destroyed bacterial colonies that should have thrived. Fleming saw that zone and asked why. Florey and Chain saw Fleming's papers and asked how to make it useful. American researchers saw the production problems and asked how to scale up. Military doctors saw wounded soldiers and asked how to save them. Each question led to the next. Each answer enabled the following breakthrough. The compound fracture soldier at Bushnell General Hospital, who received penicillin in early 1943, expected to lose his leg. Osteomyelitis had set into the bone. Sulfa drugs had failed. Amputation was the only option left. Then came the injection, the brownish liquid entering his vein, the same substance that had saved Alexander for 5 days before supplies ran out. But this time, supplies didn't run out. The injections continued. The infection retreated. The bone began to heal. Months later, that soldier walked out of the hospital on both legs. That was new. That had never happened before in military medicine. The North African soldier who took shrapnel through his chest in April 1943 should have died from pneumonia. Chest wounds in the desert became infected almost universally. The combination of tissue damage, dirt, and bacteria created infections that overwhelmed every drug available. Florey examined the soldier, cleaned the wound, prescribed penicillin. 3 days later, the soldier was sitting up. The lung infection that should have killed him had cleared. The wound showed healthy granulation tissue, the pink new growth that indicates healing. Florey documented the case, added it to his growing file of successful treatments, continued his trials. The D-Day casualty evacuated to England on June 8, 1944, had taken machine gun fire through his abdomen. The bullets had perforated his intestines, spilling gut bacteria into his peritoneal cavity. In World War I, that wound meant death from peritonitis within a week. In World War II, with penicillin, it meant surgery to repair the perforations, followed by injections every 4 hours, followed by transfer to a regional hospital for continued treatment. The soldier survived. The infection that should have killed him never materialized because penicillin prevented it. These were not miracles in the supernatural sense. They were miracles in the medical sense, outcomes that seemed impossible based on prior experience but became routine once the right tool became available. The tool was penicillin. The availability was the result of years of work by researchers, industrialists, government officials, and military planners who collectively solved the problem of turning a laboratory curiosity into a battlefield medicine. The human cost of the delay is incalculable. From Fleming's discovery in 1928 to widespread availability in 1944, 16 years elapsed. How many people died from bacterial infections during those years? How many soldiers in how many wars? How many children with pneumonia? How many women with childbirth fever? How many routine infections that became septicemia? The number runs to millions, certainly, perhaps tens of millions. They died because the drug that could have saved them existed but wasn't available, because production problems weren't solved, because pharmaceutical industry didn't commit, because funding wasn't allocated, because the urgency wasn't recognized until war created demand that couldn't be ignored. That is the other lesson. War is terrible. War creates conditions where innovation accelerates because the stakes are clear and the funding follows. Penicillin existed before World War II began. It became available during the war because military planners recognized its value and devoted resources to production. Would peacetime have generated the same urgency? Perhaps eventually. But eventually means waiting, and waiting means death for people who could have been saved. The soldiers who received penicillin in 1943 and 1944 didn't know they were part of a medical revolution. They knew they were wounded. They knew they received injections. They knew they felt better instead of worse. The broader implications, the historical significance, the fact that they were benefiting from a drug ignored for more than a decade, these were not part of their experience. They lived because penicillin worked. That was enough. But for the doctors who had practiced medicine before penicillin, the change was staggering. Infections they had watched kill patients throughout their careers suddenly became treatable. The helplessness that had characterized pre-antibiotic medicine, the experience of watching patients die because no effective treatment existed, that ended. The psychological impact on medical practice was profound. Doctors who had learned to accept bacterial infection as uncontrollable force suddenly possessed a weapon against it. Medicine changed from supportive care, keeping patients comfortable while infection ran its course, to intervention, actively destroying the bacteria before they could destroy the patient. The bacterial infections didn't know they had become curable. They attacked tissue with the same mechanisms that had worked for millions of years of evolutionary history. Staphylococcus produced toxins. Streptococcus invaded tissue planes. Clostridia generated gas gangrene. But then came the penicillin molecule, binding to bacterial cell wall synthesis enzymes, preventing cell division, causing bacterial death through cell wall failure. The bacteria had no defense. They had never encountered this molecule before. Natural selection hadn't had time to generate resistance. They died. Fleming had warned about resistance. He had demonstrated in his laboratory that bacteria exposed to subtherapeutic penicillin doses developed resistance. He had noted that resistant bacteria passed their resistance to offspring. He was ahead of his time in understanding that antibiotics created selection pressure for resistance evolution. But in 1944, with soldiers dying from infected wounds, Resistance was a theoretical future problem. Saving lives was an immediate present necessity. The decision to use penicillin widely, despite resistance concerns, was correct by any reasonable calculation. The lives saved numbered in the hundreds of thousands immediately and millions subsequently. Resistance did emerge eventually, as Fleming predicted. Penicillin-resistant staphylococci appeared within years. Medicine responded by developing additional antibiotics, by using combination therapy, by reserving certain drugs for resistant infections. The arms race between antibiotics and bacterial resistance continues today, but that race exists because antibiotics work. The alternative, returning to pre-antibiotic medicine where bacterial infection meant death, is unacceptable. The mold juice that medical authorities ignored for more than a decade established the template for antibiotic discovery. After penicillin proved that antibacterial substances could be extracted, purified, mass-produced, and used clinically, researchers began systematic searches for additional antibiotics. Streptomycin, isolated from soil bacteria, became available in the mid-1940s. It treated tuberculosis, a disease that penicillin didn't affect. Additional antibiotics followed: tetracycline, erythromycin, chloramphenicol, each with its own spectrum of activity, each adding to the arsenal against bacterial infection. The 15 soldiers referenced in historical accounts who survived infections within days after penicillin treatment were part of larger clinical trials, unnamed beneficiaries of a drug that transformed from laboratory curiosity to battlefield medicine. Whether they were among the orthopedic patients at Bushnell General Hospital in 1943, or wounded troops treated by Florey in North Africa, or D-Day casualties evacuated to England, they represented the validation of everything Fleming had discovered, everything Florey and Chain had developed, everything American industry had learned to produce. They lived because someone looked at a contaminated culture plate and asked a question, because someone else read about that question and wondered if it could be answered practically, because industrialists committed factories to production, because government officials allocated resources, because military doctors applied the drug to wounded soldiers and documented the results. The story of penicillin is the story of science translating to medicine, but it's also the story of obstacles overcome through persistence, institutional resistance broken by evidence, and individual decisions accumulating to create transformation. Fleming's discovery was necessary, but not sufficient. Florey's development was crucial, but incomplete, without production. American mass production was pointless without distribution systems and trained medical personnel. Every step mattered. Every delay cost lives. Every breakthrough saved lives. The mold juice they ignored became the drug that saved hundreds of thousands in World War II and millions afterward. The clear zone around that fuzzy colony on Fleming's contaminated culture plate expanded to encompass all of medicine, redefining what was possible, what was treatable, what was survivable. From laboratory accident to battlefield medicine to peacetime miracle drug, penicillin traveled a path that should have been faster, but was revolutionary nonetheless. The soldiers who received it, who healed when they should have died, who kept their limbs when they should have lost them, who went home when they should have been buried, they were the proof that mold juice deserved attention all along. The authorities finally listened. The timing was almost too late, but almost only counts in horseshoes and hand grenades. In medicine, almost is the difference between Albert Alexander dying in March 1941 and D-Day casualties surviving in June 1944. Almost is the sound of possibility becoming reality, one injection at a time.